I'd like to introduce Prajukti Bhattacharyya, Professor of Geology in the Geology, Geography and Environmental Science Department. She's going to talk about looking at sulfide mining in Wisconsin through environmental, social, and economic lenses. A little bit about Prajukti. She's a professor and she received her PhD from the University of Minnesota in 2000. Her background is in hard rock geology and geoscience education. She teaches courses on volcanoes, mountain building, rocks and minerals, plate tectonics, and environmental geology. Her research interests range from geochemical analyses and igneous and metamorphic rocks to volcanic activities. She's also involved in STEM education research, especially in ways to help students learn and assessment of student learning. She did speak with us years ago in the in-person scholarly scoop. You might have remembered a long time ago if you attended, where she passed out muffins and we broke into the muffins like we would break into earth looking for fossils. So Prajukti, I'm going to go ahead and stop sharing, and then please share your own screen and take it from here.
Thanks, Lida. Good morning, everyone. I'm excited to be back, even though it's virtual, but this is one of my favorite things to do, to talk to people who are interested in different fields. And I'm gonna start my presentation. I'll share my screen, but if you have a question or something, please feel free to kind of stop me and ask. So I welcome discussions and questions, and this is kind of a topic that's timely. This is happening in Wisconsin, so your feedback, input, and thoughts are highly appreciated and welcome. So I'm gonna start sharing screen. Is that okay?
Yes, go ahead.
All right. So this topic that I'm talking about is sulfide mining for metallic sulfide minerals in Wisconsin, which is different from oxide minerals. And mining is loaded. It's multi-perspective. It has environmental consequences, economic consequences, and social consequences. So this topic cannot be really talked about through just one voice. Multiple voices come in. So if we look at mining, or especially metal mining, we need metals. Now, mineral resources like copper, zinc, lead, iron, all these metal resources, they control every aspect of our society, including in our daily lives, in our kitchen, to making military warships, to everything. Now, rocks and minerals, this is something I study and I teach and I talk about. Their properties control what they're going to be used for. So if your electronic chips uses minerals that have very different properties than what you use in making your countertops, or these uses lead to demand. So different minerals used and their demand that uses control that demand, and that leads to which minerals are going to be mined and explored and processed. So for example, right now there is a demand for electric cars, and that demand is leading to making more computer chips, which is leading to more exploration for rare earth or critical minerals to make those computer chips. So the supply chain can do that. So all these use demand leading to exploration and mining. And the moment you do exploration and mining, we are looking at environmental impacts. Some mine requires you dig a deep hole in the ground. That has their own impact. Economic impact, they create jobs, or maybe they also drop the real estate values in an area that's being mined. That has social impacts. Where are you mining? Who's getting the jobs? Who's having to deal with the mine waste dumps? So all these impacts, they in turn kind of control where the exploration and mining and the processing activities are going to be. So they kind of come back to it. Now, a lot of other things like the cost, where the minerals are available, what kind of policy you are making, population growth that controls demand, all of them adds to demand besides the use of the minerals. Now, those availability, policy, population growth, and all those, they control economic impact. People want this iPhone, whatever version that is out there. That demand is leading to the exploration and mining and the economic impacts of that. So the economy controls policy and demand. Now, the exploration and mining and processing will depend on the properties of rocks and minerals. We don't explore for iron the same way we explore for coal or neodymium. So their properties, the exploration style that we use will depend on the rocks and minerals properties. The rocks and minerals properties will also control the environmental impacts. Sulfide mining, for example, has very different impacts than oxide mining or pure mining, like native element mining. So their properties control the environmental impacts. Now the geologic processes, this is my background.
That's another one.
What?
There's a lot of boxes. My dad and I, we were enjoying all the boxes. Go ahead, sorry.
Every one of these boxes require almost an entire class to deal with. And this is what I teach. This is what I talk about.
It makes sense. Thank you.
This is how, this is this kind of concept mapping. When you go about mining, it's not just one thing, it's multifaceted. And I did not add one box that I thought of, but I did not, that's time. What are the short-term and long-term impacts? So I'm not even going to talk about that, because then I'll just not move forward to any other slide except for this one slide. So that's why I'm just going to focus on this one box in the center. Everything else kind of goes like, just to make you aware that all of them has interactions to make that one thing happen. But that's the exploration, mining, and processing is the one that's most visible. That somebody digs a hole in your backyard, you know it, you see it, and you talk about it. But all the other things that goes behind the scenes work that goes into where you dig the hole and how deep you go and all these, I'm going to put it out there that it is not just one like black and white issue. It's a multifaceted issue, and it takes physical sciences, political science, social science, everything that goes into this. So just to give you a context of that, I cannot talk about everything, just that's my background and expertise.
Thank you.
So yeah, Leda, if you want to have a series on just mining, count me.
Yeah, I can see where we would have lots to talk about throughout the year. Yeah.
And this is happening in Wisconsin right now.
Right, yeah.
Because of the sulfide mining, they just removed the moratorium. They're talking about all these issues. There was a moratorium on sulfide mining because of the environmental impacts. So they removed it in 2017. January 2021, they kind of approved some of the regulations, what the mining companies have to deal with. Every one of those boxes and arrows went into that before even start about exploration. Yeah. That's the background. So moving on about exploration, mining, and processing, that's the mining cycle. Mining cycle starts with exploration. As a field geologist, that's primarily my background and my job. So we look around, go do the geologic work to explore, to find where the ore minerals are located. Once that's located, that's done, then the mining happens, that's the extraction. Different ways of mining happens. Now beneficiation is when you extract the raw ore, then you crush it and grind it and get the metal out of that raw ore. Now that may or may not happen on site. So I don't know how much time I'll have to talk about that. It's kind of off-site, so we can put it out of that. And then once the exploration and extraction is done, you reclaim the mine to close it up. So this is what I talk about when I teach my students about this. This is what, like, my approach to this is like the same approach that if somebody goes to a doctor for donating a kidney. So when you're donating a kidney, somebody else needs the kidney, otherwise you won't be donating it. We need the metal. So when the doctor looks at the person who's the donor, the doctor better be very respectful, do a lot of the non-invasive procedure to make sure where they're going to incise. And then when they make the operation, that's the extraction, be as little damage as possible, go in, take whatever they need to take out, and then don't do more damage than necessary, and then have a reclamation or a recovery process set out so the person who's donating it doesn't suffer unnecessary health impacts. That's kind of the way I teach my students to treat the whole mining cycle. Like, imagine you are a doctor, you need the metal, but treat the planet as if the planet is donating that organ for your benefit. So treat it with respect, don't do more damage than necessary, and make sure whatever damage you do, every surgery does some damage, but whatever damage you do can be recovered from without kind of adding on to that damage. Now that's different from body snatching and organ black market. There are people who get kidnapped and their organs get taken out and they're left to die. That's the type of mining, you go in and you destroy the environment and just take it out and leave the area to just, like a mess, is not okay. And that's kind of how I talk about the mining cycle. That's my approach. Because as a geologist, I do both sides, the exploration, extraction, and the reclamation process. So it's a overall holistic process that I'm kind of going through. Exploration, we look at geologic maps, we look at cross sections, we study these details that's out there. This is the non-invasive process that you compare the similar environments where things are happening today, where things happened in the past, and you compare those things. We do field studies that can be like detailed mapping, some invasive geophysical mapping, surface rock sampling, chemical analysis, go back. That's just the exploration. For exploration geologists, our results will invite a company to think, any idea how much money goes into just making a mine? The investment in a mine, like how much money is running on this exploration?
No clue.
Think billion, several hundred million just to do the exploration, and that's before that's a hole is sunk. Just to get the exploration, getting the land purchased, getting all the regulations, doing more explorations, doing seismic exploration, all those, almost $1 billion just goes into the exploration process, and that's even before they gotten anything out of it. Yeah. So when you're an exploration geologist, if you don't do your job well, you don't keep a job. And so you have to be very careful on that. So that has a lot of non-invasive studies, because the moment you start drilling, you're sinking even more money in that, because drilling, operation cost, and everything comes into play. You're paying a lot of experts for their time. So that's a big investment right there. Seismic is using earthquake waves to figure out where you are targeting, how deep you're going to go in. Magnetic studies, depending on what metal you're doing. So these are non-invasive. You pinpoint to figure out where your ore material is before you even drill anything, because the moment you start drilling, it is like you're doing a surgical operation. You are actually making an incision. Before you get there, you need to make sure you know where you're doing and what you're doing and how you're doing it. So this is a drill code that I took a example when the Eagle Mine, Yellow Dog, Michigan, that's a gold. There is nothing on the surface. That's just a dump, like a wetland. Underground, it's fascinating. We went in there when the project was in the preliminary stage, like a proposal stage. So they just drilled out some cores and they made a model of how they're going to mine it and where the ore is based on their non-invasive procedure and some of the exploratory drill core. This drill core right here, the brownish part is copper and zinc. The goldish area is pyrite, that's iron sulfide. And there is a lot of precious metals, the platinum group elements, there are tons of them right in these areas. So this is how you get an estimate of how much metal you can recover from that ore. So cost benefit analysis, this is where you do it. And this is also a place for, do you really want to drill in there or do you want to get away because of the environmental impacts? Like, is it worth going in? So you do all these exploration, do some drilling. The taconite mine in Wisconsin went into the drilling phase, and then they saw some asbestiform mineral, that minerals that have a form of asbestos. You drill it and you get the same kind of mineral that's asbestos out in the air. That's a huge possibility of air pollution. So the company just backed out, like, no, we are not dealing with that. So the exploration is done, and this is a lot of mine that gets kind of put on hold, or the company just bails after sinking all this money into the exploration. So that can happen. Even after the drilling, you have to make sure that it is financially viable. And that depends on a lot of non-geology. So how much mineral is in there? How deep you have to drill. The more deeper you go, the more money you're sinking in here because the extraction process is going to cost you money. Do you have the technology to go in there? What are the potential environmental impacts? And this is a huge issue right there. Now, this image I have here, it's a USGS scientist is sampling metal-rich water. This water is completely polluted from a pile of mine waste was left out in the open before there was any regulation of how to dump your mine waste. The water got seeping out of that. And yeah, that water, I would not recommend anybody drink it, but I cannot stop animals and plants from drinking it because it is there. And this water has so much heavy metals in them, like arsenic and lead and cyanide and all those. So this is a huge environmental hazard right there. So we want to avoid anything like that. This is the recovery process. We don't want to have anything causing more problem after the mining is done. We also look at transportation and water needs. Mining takes a lot of water. Now, do you have enough water to continue mine without taking out drinking water from local communities or without destroying a river or a wetland or something? Transportation, do you have enough roads to have all these big trucks taking material from the mine to the processing plant? That is a big problem. Like you think of the frac sand mines, they are taking sand out and supplying it to Texas. But the trucks that are carrying those multi-ton of sand are destroying the roads because the roads are not built to carry that much weight. So now the local communities don't have the quality of their roads are going down. Now, who pays for that? So all these issues have to come to play before you even start a mine. Regulations, now this goes from state to state, county to county. What are the regulations in there? Political boundaries, the local politics, this becomes a huge issue. Social norms. Are you mining in a Native American reservation and nearby? Where are you dumping your mine waste? You want to be very careful about what the social norms. Are you doing it in the middle of a town or a state park or a tribal ground and the last but definitely not the least, human health concerns. You're mining something. Is that going to impact the health of the neighborhood? That could imply that sound pollution. What would do the all continuous drilling sound or blasting sound? The air pollution, when you dig something, are you creating a lot of dust in there? What's that going to do? Water pollution, definitely. Uh, Aesthetic pollution, well, you got a house for a beautiful view. Now all you see is a drill rig in front of you. What's that going to do to your mental health, your emotional health, and not to mention your value of your house? The market value goes up or down. What's happening to the green space that used to be for people to hike or recreation, but now there's a mine? How's that going to impact people's emotional or physical health? So all these issues come to play. This is where the sulfide mining is right now. They're having these conversations, hopefully with different stakeholders. My job is done. As a geologist, I'm focused on the first one, the concentration of mine and depth to ore. Then I give off to engineers, and then I do a little bit in the environmental impacts, but I leave that to the DNR, the biologist, to have a bigger picture. So lots of different perspectives. When I say economic, social, and environmental lenses, this is what I was trying to kind of bring out, that everybody need to have their voices be heard. And that's still exploration. You haven't sunk a drill, like a mining drill core yet. So once all these kind of get settled and people decide, okay, doing the mine, if you have a good plan, we know what you're gonna do. You're gonna go in, take out what you need. This is how long the mine is gonna be, how many ever years, and then after that, we are gonna reclaim this. This is how we are gonna monitor the water afterwards. This is how we are gonna plan and bring the land back to semi-normal state. Once all this is done, we start the extraction process. That's where the actual mining happens. Two different ways. The first one is surface mining. This is the mountaintop removal or open pit. Basically, you're digging a deep hole in the ground. This is the Kennecott, Utah copper mine. This is the biggest surface mine in the planet, the biggest hole. You can see it from space. It's a copper mine, still active, as opposed to the underground mine, the shaft mine that's drilling down, making a deep hole. Sometimes the same mine will have both processes, like you start with underground mine, then make a surface mine in one spot, keep doing the underground mine somewhere else. Underground mines used to be more common until the 1900. So it's like the dwarf, you take a little shove, a little ice pick and a mule and dig into the mountain and then dig out your whatever you're mining out. Badger State, Wisconsin got its name, the Badger State, because of these little individual mines for lead in the lead zinc district down in southern Wisconsin. Miners will go in, dig a little hole. They put their little, they'd live in the hole for winter, and then dig their holes in summer. So they will have little badger holes all over the ground, which is the Badger State. And Wisconsin got the lead miner in the Wisconsin state symbol. So mining and Wisconsin history are kind of interconnected. That was a lot of underground mine, but today we have big equipment that can remove a lot of earth, make a big hole. So that's the more common way of mining. The surface mine is easy. You just go dig out everything. This is a golden sunlight mine pit. This is approximately 100 acres, this size right here. This is the actual mine right here. And all these other holes are waste rock. This is a gold mine. So they took out the gold particles. They're like really tiny nuggets or even microscopic in some case. But once you take it out, you dump out your liquid waste in the tailing ponds and solid waste in the dump complex. So the mine itself, this is 100 acres. So you can imagine how much of the land has been disturbed by just that one mine, which means all the trees and anything, animal habitats are gone. Any kind of surface water that was out there, that's not there anymore. Any other kind of land use that was supposed to be, they're all gone. And so all this land, it is just disturbed in what it used to be. Lot of waste materials, so 2 to 3 tons of waste per each ton of ore mined. This is the more common way of mining right now. Underground mine, on the other hand, now this is the deepest underground mine, another gold mine in South Dakota. So you can see there's a lot of tunnels and shafts. There are air exhausts. Ore pocket is right here. They know the depth and where it is. But to get there, you don't drill one straight hole. You have a lot of different shafts. Security or mine safety is a big concern there. Safety, as in you don't want a mine to collapse and kill your miners. So that's one of the big concerns there. So you have a lot of air exhaust, different ways of coming in and going out. So that's underground mine. It's a lot smaller. The like you're going in for a little payload. Tunnels and vertical shafts are much less environmental footprint. The land disturbance is much lower than surface mine. So this is the two different, there are pros and cons of both. Surface mine is safer. Miners don't, their safety is not that much impacted by surface mine. Underground mine, any time you hear about mine collapse or miners are trapped in a mine, it's an underground mine. But the environmental impact of underground mine is much less than surface mine. So pros and cons to both. Less waste rock for underground mines. So that's another good thing about underground mines if you're into the environmental the aspect of it. So what's all these have to do with Wisconsin? This is the bedrock geology of Wisconsin. This is under the glacial deposits there. So this is the rocks that we see if you remove all the stuff that glaciers brought in. We are right here in Whitewater, southern Wisconsin area. This is more limestone, dolomite, rocks that are deposited from the oceans. Up north, this used to be a ocean floor. All these areas used to be volcanoes and volcanic island arcs. So this is the first stage of exploration. You look at the geologic map. Now, when you look at the geologic map of Wisconsin, we are actually looking at a bunch of little continents that are stuck together as the bedrock was forming. So the bedrock, some of these rocks are almost 3 billion years old. This Lake Superior mid-continental rift, that's about 1 billion years old. Rocks in here, the Yavapai province and the Pembine Wasa terrain, these are about 2 billion years old. These rocks in the Archean craton are about 3.5 billion years old. So you're talking really old rocks here. And this is the bedrock, the foundation of Wisconsin. Parts of little continents got stuck together. Yeah. It makes me feel so young, you know? I'm looking at rocks that are billions of years old. I'm like, I don't care. I'm just a young pup. So how did all this get together? So when you look at the geologic history of Wisconsin, we are looking at right here 3 different pieces of landmass. Superior Province, that's the original craton, the bedrock. These areas were volcanic islands, and these areas are another part of another continent. So how did we all get together? This is what Wisconsin looks like. You got original cratons up here. In the middle, there are a lot of volcanic islands stuck between these two continental pieces. So what happened, if you go from north to south, there used to be an ocean, and we're talking billions of years ago. These rocks, this is my research area, there is Pinocchio and orogeny, the volcanic island arcs there. So there used to be volcanoes just like there is in Hawaii, not Hawaii, Japan right now, today, equivalent in tectonics. This is Minnesota and Canada up north. There used to be an ocean, and then you have islands with volcanoes coming towards the continent. So this is what current research shows. This is from a paper that's published in 2007. Schulz and Cannon, about 1890 million years. So that is about 2 billion years ago. You used to have volcanic island. This is the Pembine and Wassaw terrain. The island started coming towards the craton, then they got stuck. There is another ocean behind it. Then this ocean starts to sink, and then eventually about 1850 million years ago, Wisconsin, the northern part of Wisconsin, became what it is today. All the areas, the little bits and pieces got stuck together. Now here it says location of VMS deposits. This is where you have sulfide deposits today. These are the mineral ores that we are looking at and to dig out. That used to be islands, volcanic islands, once upon a time. So why volcanic islands and sulfide ore? This is Hawaii today. This is Halemaumau Craton. I've never met a volcano I didn't like, so I work a lot on volcanoes. That goes from Hawaii to Iceland to Montserrat, you name it, I'll be there. If a volcano, I will be happy to visit it. So in volcanoes, you have hot magma underground, and rainwater, groundwater, seawater, any kind of water that goes through cracks that get heated by the magma and also mixes with other gases like chlorine, hydrogen sulfide, sulfur dioxide, carbon dioxide, fluorine. You go into a volcano, you see this steam coming up. Go to Yellowstone or Hawaii, you have these geysers, stink of sulfur. So all these volcanoes have this sulfur and other chemicals in there. And this is what we call the hydrothermal fluid. Hydro as in water, thermal as in hot. So basically we are having hot water in volcanoes. 90% plus of these gases are water vapor, plus other things. So every volcano will have hydrothermal fluid. That's kind of what volcanoes do. They take water from the surface, heat them up. Now, what happens to these hydrothermal fluids? This is another photo of near the Kilauea caldera. You see these yellow stains there, that's sulfur. So the gases are bringing out sulfur from the magma, kind of cleaning out the sulfur and then dumping it when the water vapor becomes liquid water. So right where the vapor cannot carry the sulfur, they become solid sulfur crystals. A lot of the metals are in the magma as well with the rocks. So metals like copper, nickel, lead, zinc, silver, gold, platinum, all these type of metals, they get kind of leached out in the hydrothermal fluids. The hot water, basically, just like you clean your driveway with a hot spray when you are cleaning for car oil or something, hot water takes out all these metals. They react with the sulfur that's out there and then become sulfide metal ores. So wherever you have a volcano, you can expect some sulfur, and the metals that are in the volcanic water becomes part of that sulfur, reacts with it, sulfide, metallic sulfide ore. It's happening today. These kind of ores are forming in Japan, which is how we know what to do with Wisconsin, because it's very similar. Doesn't matter it's 2 billion years old or happening right now. The process is the same. So you look at Hawaii, look at Yellowstone, look at Iceland. We know how the sulfide formation happens, and we bring that to Wisconsin. So this is the map. This is the metallic mining project. I got this map from the Department of Natural Resources. Current projects, Flambeau, closed right now. But then you have Lynn deposit up here, Crandon and Michigan back 40. So that is in one line right here. And then you have Bend and Reef. That's also part of this kind of at an angle. All of these have metallic sulfur because this was part of a volcanic island arc. There's lots of volcanoes 2 billion years ago. Now they have those metallic sulfide deposits formed as part of the volcanic process. This is the lead zinc district in Wisconsin. This is where the Wisconsin got its name as the Badger State from lead mine. This is a whole different process of mining, ore formation. And maybe a next lecture, we'll talk about how these metals formed here. So I'm going to focus more on these mines up in the northern Wisconsin, because these are part of the current discussion. Nobody's talking about this, developing these mines anymore. So up north, up here, Lynn deposit, primarily zinc, a lot of lead and silver, little amount of gold and copper, and they're planning an open pit mine there. That's in Oneida County right here. Then you have Crandon, 55 million tons of zinc, copper, lead, gold, and silver. So the tribes, the Chippewa and Potawatomi tribes purchased this site and they're keeping it. They're not talking about developing these mines, but it is a pretty good reserve right there, 55 million tons of all these metals. Bend, huge gold mine. Bend has such a huge amount of gold. It's probably going to be an underground mine. It's a little bit of silver, but not lead or zinc. So we are talking precious metals in Bend. Reef, more about 500,000 tons of high-grade gold right there. It's going to be an open pit mine when they develop it. So this is why I'm bringing out the economic aspect of it. We are talking a lot of really pricey precious metals sitting right there. So a lot of people are like, hey, let's develop those mines. Michigan back 40, it's not in Wisconsin, but it's right here across the river. It's almost, they're going through their Department of Environmental Quality, the DEQ, and looking at what kind of mine. They're planning an open pit, and they're also planning to process the mine, the zinc and gold on site. And they're going back and forth with water quality and what's going to happen with downstream water. And so this is in the process of being developed right now, and Wisconsin is going to look in at it because it is right across the river. Anything happens environmental impact wise is going to impact Wisconsin, but Wisconsin is not part of the discussion of anything else. Last I saw, they said the water quality is like it will pass Wisconsin's water quality rules, but I didn't see any details of what exactly they're looking at. But this is also a big gold deposit with some zinc. So all these mines that are up there, people are getting a lot interested. Once the moratorium was lifted, there are a lot of mining companies are looking at it as a good economic investment right there. Now I'm going to put the native tribe map right there. We talked about the Crandon mine already being bought out by the Potawatomi and the tribes up there. So they are not looking at it to develop it. But there are other mines that are also close to some of the native reservations. So this is where the conversation is right now. So people are looking at, like, if you're developing a mine, who should be the stakeholder and who should have a voice in the discussion and a place in the table to figure out where they're going to develop, how they're going to impact hunting, fishing, gathering, and all those activities, sacred land. And how do you talk about the infrastructure and transportation and road building and all these requests, cutting down trees and, you know, diverting rivers and streams, putting dams there. So this is where the social and environmental aspects, this is where the conversation is right now. So the environmental aspects of it, this is what happens with sulfide waste rock. Now, this is some of these photos that I'm going to show that will make you cringe, that happened in the 90s, where the regulations are not as it is today, because we learned from our own mistakes, right? So this was a waste pile of a gold mine that was dumped into a floodplain. And when I showed this photo to my students, they visibly cringed. Like, why would you even do that? Now we know, hindsight is 2020, why it is a bad idea. But in 1993, nobody cared. And we are paying a lot of price because a lot of the practices that happened in those days. So what happens in sulfide mines? That we have sulfide. There's the good news and the bad news. Now, when you have sulfide, especially iron sulfide, and you leave it exposed out in the air and water, they react. That's their nature. Now they react with water and anywhere. And when you react iron sulfide like pyrite with water, you make sulfuric acid, that's battery acid, which is again natural because that's the nature of sulfur. Sulfides react with water. But when you let it happen there, we are turning groundwater or stream water extremely acidic. Now, this mine waste that was dumped into in a floodplain, in, you know, exposed to air and water and all those, now these become Superfund sites. Today, we have a lot more regulation of placements, water flow. How do you monitor it? How do you, make sure that these sulfide waste don't get into water? But we always have to be very vigilant that this doesn't happen. Again, I'll have pictures of, you see water, this green, it's not pure water. This is algae. This algae only grows when the water has a certain acidity. So when you see this kind of green water or blue water, you don't jump in there. It's acidic water. There is nothing can grow. Every other habitat is destroyed. So when you have sulfide, these pyrite are sulfide minerals that react with oxygen in the presence of bacteria. It has its own little chemistry lab and makes sulfuric acid. Sulfuric acid will do a lot of things to iron, that will leach out iron, turns into rust. And basically, when you have fish or frog that lays eggs on the shallow water, or any other animals that needs that water for surviving, you're putting them in an acid bath. So if you don't control it, it becomes a problem like this. So this is in Colorado. This photo is taken in 2016, old mine dump that got some manganese oxide coating on top. So this river right here, this drainage is no acid. This one is leaching out of the mine dump. You see the color? That's your acid rock drainage. That's taking out, leaching out iron from there and basically killing any animal that can live, or any plant that can live in these rivers. So Tale of Two Cities, acid mine drainage, that should have been like this. Now the same mine, it's closed. This mine is closed. The mining company just did their dump. They left. Now EPA went in to do some exploration about how to do that. They accidentally leached the mine waste into the Animas River. This happened in 2015. I'm not going to say anything. I'll let you look at the before and after photo, how it used to be, and before and after the mine waste went into the river. So when you look at Wisconsin sulfide mine, this is what you're trying to avoid. That we make sure that the mine waste are put in a way that our rivers, this used to be a trout river once upon a time, not today anymore. Fish can't survive there. And nobody's gonna go hiking or canoeing or anything in that river because of that water. And that's just, I don't see myself swimming in there. So the recreation industry that was around the river took a big hit. The water quality apparently is coming back in 2021, but I'll give it a few more years before it will become this pristine blue color.
And you said that was caused from the EPA did that?
Yeah, which is kind of ironic, right?
Yeah.
Yeah, the mining company kind of had their waste in like a tailing pond. EPA went in there in 2015 and they're just exploring, like trying to figure out how to clean it. And somebody poked a hole in the tailing pond wall and everything, trying to see 3 million gallons of wastewater went into the river. I said, I'm not going to say
That's
anything.
crazy.
I have no words. And this is what happened when EPA went in there. So now they're responsible for cleaning it up. But once the water is out there, it's the cat is out of the bag, right?
And isn't cleanup just a matter of time? There is no cleanup. I mean, what can they do to clean up? They just have to wait, don't they?
Exactly.
Yeah, so cleanup is sort of a silly word. They're not
Exactly.
really doing anything. Okay.
So basically they're sitting there waiting for the acid to kind of disappear by itself. But while they're doing that, a lot of the economic impact, you can think of any tourist industry that used to be out there, any fishing, hunting, anything that used to be out there. Anybody wanted to buy a house out there? Like I feel bad for this house, sitting right here. Anybody wanted to have their house valuing any outdoor recreation sport? Now, if you're just sitting here waiting for it to become natural again, but all these impacts add up and that goes to the people. So by the time this becomes pristine again, it's 2015, maybe by 2025. But what's going to happen to that area in the next 10 years or in the meantime? So no, cleaning up is kind of a spinning your wheel. You basically wait for the nature to take care of it. And my thing is like prevention is better than the cure. I don't want this to happen. So I'll stop it before this kind of things happen anywhere where I live. So the way people do that, this is, you take the pyrite rocks that causes the acid drainage, bury it down under soil layer, you pack it down and put plants on it. Don't let oxygen come in contact with the acid. Make wetlands. This is a big deal in Wisconsin. The mining companies are looking at, are you destroying the wetlands or are you creating more? Wetlands function as kidneys in our body, so they kind of filter out the pollutants. Same with acidic heavy metal. You pass the water through a wetland, the wetland cleans out the water and filters back the clean water out. So this is a natural process. The bacteria and the plants, they kind of clean the water out.
How does that happen? Because like wouldn't the metals be polluting that water though?
They get precipitated out in the bottom.
Oh, okay.
So they get separated out from the water.
That makes sense. Yeah. Okay.
So Wisconsin wetlands are, I'm so glad that Wisconsin cares about the wetland, because the reeds and the plants that pretty much acts like filters, kind of separates the water, keeps it in the sediment under the wetland, and the water that goes into your groundwater well or your river water that becomes less or free of the heavy metals that are out in there. And the companies are now, I think they're required to create wetlands. If they destroy one, they have to create one. That has some issues there too. Like, how do you know that the one that you're creating is just as effectful as the original one? But it is a viable solution. People also add lime. Lime takes out the acid. It is the same process that you take Tums or Alka-Seltzer when you have acid reflux. Your stomach acid gets neutralized by lime, like a calcium carbonate. And the same thing you do in the soil. So you have acid, you put some lime in there, the acid gets neutralized, it becomes pure water. Then you run the water through a treatment plant, and then pass it back onto the wetland or stream or whatever. So you take out the heavy metals from out there.
Can I just clarify, are you saying that when the mining companies engage in all of this extraction or whatever, and they have to also now include in that process the creation of a wetland or this waste rock treatment plan? And so is this regulated? Are they required to do it, or is it is? Okay, thank you.
This is what we learned from the 1990s, that you hold the mining companies responsible. So how are you going to pull that? What's your reclamation plan? And that has to be included in your environmental impact plan. If you have tons of time in your hand, this is like 12 volumes of environmental reclamation that goes in, like how are you going to control your biological impacts, water, and all these. What's your reclamation plan? How do you monitor it? So the company is also responsible for monitoring your water level, as in the pollution level in the water, to see if anything is leaching or leaching out. So nobody goes in there trying to poke around, exploring, and then poke a hole. And guess what? 3 million tons of wastewater is out there. So these are all included in all the mining companies' plans. And again, multiple stakeholders has to look through these, because some of these things are so convoluted that if you don't have a background in what you're reading, you can get lost. I looked at the back 40 mine, the environmental impact plan, and I had to really look for how they're gonna what is the way they're processing their gold. And I know what I'm looking for, and I had to kind of comb through all this to see, oh, they didn't talk about it. Now somebody has to mention that they didn't talk about what they're gonna do for that. They talk a lot about biology, but they don't talk about the geology part. Now somebody without a geology background is say, oh yeah, they're talking about biology, that should be fine. But no, how are you gonna get rid of the cyanide that you're using? So a lot of different eyes should be on the environmental impact plan, which I'd strongly recommend. So yes, all these things should be in a mining company's plan. And this also takes their money. So you have to invest, like you have to show that this is how much of the profit is going towards land reclamation. And if not, please don't let them mine here. So what's my role in this personal thing? This is what's happening in Whitewater, in our Upham Hall. So we got some sample rocks from Lynn and Flambeau. And this is what the ore looks like, actually. You get this one layer right here that's zinc rich, some quartz from the hydrothermal. This is copper a little bit. This is a lead layer. So this is a zinc and a lead. The gold part is pyrite. Now we put it under a microscope. This is a scanning electron microscope that we have on campus. So this is 100 micron, which is 1/10 of a millimeter. So you can see the galena and sphalerite. This is zinc, this is lead, and this is quartz. they're all on top of each other, that you cannot really separate them out by just crushing them. They're like, the lead crystals are right on zinc crystals. So we are trying to develop a process that can actually analyze, like, how do we digest sulfide ores to get a better value, how much sulfur is in there and what metals are in there. So this is our current project that kind of got sidetracked by COVID, but pre-COVID, this is what you're doing. I haven't been in the lab because the student hasn't been in the lab. So we'll come back to it in fall again. But until then, we got some samples from Lynn. This is one of the mining areas that are planning to be developed, and some from Flambeau. That's closed right now, that's been extracted. We got some pure samples of sulfur, copper iron sulfide, that's copper ore, iron sulfide, that's the environmental waste product, zinc sulfide, ore for zinc, and lead sulfide. So we took those samples, the pure crystals from my lab, we put it through a digestion process, and we compared the pure samples with the core samples, the exploratory drill core samples from Lynn and Flambeau. Our process that we are developing takes much shorter time, 20 minutes ramp time, 20 minutes hold time. The common processing that happens, each step takes at least 45 minutes, and then you have to wait for the whole thing to cool down for sample change. It takes a lot more acid. We take about 4 milliliters of nitric acid. They take 10. We have 5 milliliters of hydrochloric. They take 2. We do not take any hydrofluoric acid. We do not take any boric acid. So our process, we are cutting down the analytical cost and time. Time is money when you're processing something, because your scientist or technician is getting paid by the hour. So paying them for 20 minutes as opposed to paying them for 45 minutes make a huge difference in how much money is going into the analytical process. So yeah, this is our student Ori. This is my colleague, Dr. Enoch. We are working in getting these samples digested, like dissolved in acid, so you can run and see how much metal is in there. Iron sulfide looks this yellow, copper sulfide looks this green, so you know all the sulfides got into the solution. We run the solution. This is already doing a run in analysis. We are getting data, and our data is comparable to the EPA data. So the EPA data takes a lot of time, takes a lot more acid, that takes money to buy. So a much more pricey and time consuming analytical process. Ours is one step, and the amount of recovery that you get is pretty comparable for all the elements that the pyrite, galena, that's lead, zinc, copper, pure sulfur, they're comparable. So our accuracy is just the same with much less time and money. We don't have the silica in there, but silica is not being mined, so we don't care. We have comparable results. This is where we want to go in, because when you have it, when you have an accurate method that requires less time, fewer steps, and more cost effective, it adds to the economy. So the mining companies don't have to spend as much, and we know how much sulfur is being dumped. So it's also environmental. So we know how much lime or anything to put in to make sure the sulfur, the amount of sulfur means amount of acid that's going into rivers, so acid rock drainage. So that, if you know how much to put in, we can prevent it much better. So this is where our research is going. So we can save money and make the environmental impact a lot less than otherwise would have done. So I'm going to end on this slide because this is a positive note, and any questions or anything, I'm open for that now.
I have a couple.
Yeah.
Focusing on Taylor County, which is where I grew up, I know a little bit about it. How much influence do the tribes have because of the ceded territory? It's not on their reservations, but it's in the ceded territory. Second was some old timers like my grandpa told me that in the early 1900s, companies came around and bought the mineral rights for very low prices, and so that a mine might not do the people there today any good. How much is the federal government, because this is all national forest. Much of Taylor County is Sagamo National Forest. So I'm just curious about your comment.
The tribes are getting a voice. I don't know exactly how much influence, but I know we are, like, as an academics or academicians, we are trying to get the tribes get more involved because it's their land, period. So there are conversations that are happening between the tribal councils and the legislatures and the mining companies. That much I know, that there is a conversation that's happening, and the regulations that came out recently in January was that the mining companies had to notify the tribes when a mine happens. Now, notification and having their input are very different things. So that's how much I know, that they'll be notified, but notified what? Okay, I'm going to dig out your backyard in 7 days, deal with it. That's notification. Or notification as in, hey, we are planning about it. What do you think? And how can you do it better? That's a whole different way of notifying. So there is a conversation that's going on. And I'm so glad you brought up that issue. That is an issue that I'm trying to bring more awareness. Like, look, everybody has to have a say in this because it impacts everyone. Importantly, the tribes that are out there, that it's their land. So that's why I kind of put the tribal land map and the mining map side by side. Like, it impacts a lot of different aspects of who we are. So now I'm glad you brought up this point. And frankly, as a geologist, I really don't know, but I'm just trying to bring awareness to people who actually does work with the tribes and telling them these are the issues that you need to be worried or aware of that might happen.
And so how much power would a tribe have? You mentioned in the Crandon mine areas that the tribes purchase the land. Does that mean they can stop the mining? Or
They have.
They have stopped the mining.
Yeah. In 2003, they just got the land and everything. They own the mineral rights. And as of right now, they're not even talking about getting the Crandon mine developed or anything.
So when they don't own it, then that's where there's more of a power difference between the mining company and so on and the tribes, and one's going to win over the other.
Yep.
So do we call that environmental justice issues?
Yes. And this is kind of where my expertise ends and the social scientists take over. I can talk about the environmental impacts, what happens when sulfide goes in there, but environmental justice, I just pass the baton to social scientists. So please raise awareness or talk to the tribes, and I can talk about the science, the hard science part of it, the social science aspects, the economics, and the other dynamics, the human dynamics is a whole different issue that need to be kind of brought out.
Yeah. Well,
about 500,000 tons of gold is a huge, incentive for a lot of mining companies to go in there.
Mm-hmm.
So that Lynn deposit is kind of interesting. We did a lot of work on Lynn, but that whole area is a wetland. An entire area, the mine is under a wetland. So we went out there and visited that area, and one of my friend owns a cabin there. And I told him, like, this rock right here is worth a lot of money to a lot of people. And make sure you know what you want. Do you want your cabin in a pristine landscape or what? So conversations like that should be starting.
Okay, I think we're out of time, but I just want to thank you so much for presenting on this topic so clearly, and it was really educational for me. I hope others enjoyed it too. And I just want to remind everybody that we'll send out a eval form that we'd like you to fill out. It's just a 5 questions, 6 questions, multiple choice kind of Likert scale, so it should be easy to do. But let's say thank you to Juke for all the wonderful information she presented and leaving us on an optimistic note.